So where things get more interesting is when we also now introduce rotation into it. So now, let's imagine the star is rotating at some rate, and I also have this complicated magnetic field structure. I'm going to now simplify this complicated magnetic field structure into a theorist's monopole. Okay? So the theorist monopole, since there aren't actually monopoles, the theorist monopole is what's called a split monopole, where the magnetic field lines go out in one direction and in the other direction. So this satisfies G equals 0. There's no global monopole because the field lines are going out in one direction and in the other direction. And the way you can think of this, so this is kind of a toy model, / we'll talk about models of spinning black holes with monopole magnetic fields. It's a very simple kind of model in which the magnetic field lines have a very simple geometry, so we can actually calculate things relatively easy. We can calculate the structure of outflows along these magnetic field lines. And you can think of this as kind of an extreme limit. If you initially had these dipole magnetic field lines, like a very powerful outflow that tries to blow open magnetic field lines, what it does at large distances is it kind of approaches this monopole-like solution. Okay. So now we have our rotating star. It has some magnetic field line. I'm going to focus on studying the properties of magnetized outflows in the equator of the star, just at the symmetry point, so again, to simplify the analysis a lot. So now imagine that material, as it moves outwards, imagine that the magnetic field is infinitely strong. It's an infinitely rigid wire, so tension stuff that's outflowing actually goes up. And that is angular momentum that is being extracted from the rotation of the star. So what is happening is that the magnetic field is providing a mechanism for tapping into the angular momentum and rotational energy of the star and transferring it to this outflowing material. So this co-rotation continues out until the point where the magnetic field can no longer be treated as an infinitely stiff, infinitely rigid wire. And where is that point? So roughly, that's the point where the energy in the magnetic field is about equal to the kinetic energy of the outflow. And more specifically, the notes do a more detailed calculation. I'm going to tell you, what time did I start at? 2:15? Okay. The notes go through a more detailed calculation, which I'll sketch out a little bit of. It turns out the more detailed calculation says that the place where you stop co-rotating is where the energy in the magnetic field is about equal to the radiokinetic energy of the outflow. And the rough idea again is at this point, okay, at that point, there's so much energy now in the gas that you can't treat the magnetic field as this rigid co-rotating wire. This point is known as the Alfvén point. And it's another kind of key point describing magnetized stellar winds. So we have the sonic point, where the speed equals the speed of sound. This is the place, the Alfvén point, is the place where the speed equals the radial Alfvén speed, roughly, which is v divided by square root of 4 pi rho. And that's the point at which the co-rotation stops. Okay, so that's kind of a slightly physical or heuristic understanding of what happens in magnetized outflows. I'm going to sketch that out in a little more detail. So any questions about that physical picture? Yeah, that's right. So the phi component is also important. It turns out at this Alfvén point, the phi velocity and the radial velocity are comparable to each other. The phi velocity, or they can actually, let me check that. That depends on the properties of the outflow. But it actually is the radial velocity. We'll see that in more detailed calculations, not the phi velocity. That comes out in the more detailed calculation. Any other questions? Okay. So the model, to elaborate on this, the model is we have a rotating star. We're focusing on an outflow in the equator, again, really just for technical simplicity. And I'm going to allow the velocity to have a radial component plus a phi component. And the magnetic field also has a radial component plus a phi component. The theta components of the velocity in the magnetic field are 0 at the equator by symmetry. That's part of the nice thing about working at the equator in this model. So what we want to do now is we want to again solve our basic conservation laws to describe the property of the outflow. So just like we solved conservation of mass, momentum, and energy here, we want to now again solve conservation of mass, momentum, and energy in order to work out the properties of the outflow. So I'll just sketch out how that's done in order to introduce in a little more detail some of these ideas which were heuristically motivated here. So we again have conservation of mass, m dot is 4 pi r squared rho vr. We now have to worry about the evolution of the magnetic field. So ddt is curl of v cross v, the induction equation. So it turns out, for this setup, like ddt, we're doing a steady state outflow, there's no variation in time. So, ddt is equal to 0, so all we have to do is solve curl of v cross v equals 0. It turns out that only has a theta component. And so that's relatively straightforward to solve, so I'm going to skip the algebra is in the notes. What that implies is actually a relationship between the phi magnetic field and the radial magnetic field, which is of this form. So v phi divided by vr is equal to v phi minus r omega divided by vr. And the way to think about this physically is that, again, consider the perfectly rigidly co-rotating limit where there's no phi magnetic field. So d phi is 0 if you're perfectly co-rotating, so the phi velocity is exactly equal to r omega. What happens, though, is if d phi is less than r omega, it means the material, which has to long magnetic field lines by magnetic flux conservation, which is still not quite co-rotating, d phi is less than r omega, then the magnetic field lines actually get swept back. They can't be perfectly rigid rods anymore. They get swept back, so there's a finite d phi, which is less than 0. Okay. So then, the next equation that turns out to be important is the phi component of the momentum equation. And that, you can show with a little bit of algebra, becomes the following. So the phi component of the momentum equation tells us how does the angular momentum change. So this is the Lagrangian derivative of the angular momentum, right? It's the time rate of change in angular momentum co-moving with the fluid, and that emphasized v grad v is this co-moving derivative. This is the specific angular momentum. In hydrodynamics, it would be 0. There's no torque in this pure spherical stellar wind in hydrodynamics. But with the magnetic field, there's actually a finite torque, which takes this form. So again, this just follows writing down the momentum equation that Matt wrote down for you, and then looking at it in spherical polar coordinates at the equator. That's all I've done here. Okay, so we can integrate this equation. So if you multiply by r squared, you'll notice the left-hand side is rho r squared dr, that's m naught, that's a constant. Similarly, dr times r squared for our kind of fudgy, making nervous monopole thing is also a constant. So I can just integrate this equation. And this integral, I'll call the constant of integration L. It takes the following form. So L, which is a constant of integration for the problem, has two contributions. So this part is the angular momentum of the outflow associated with the gas. So in general, this quantity L is the specific angular momentum, the angular momentum per unit mass associated with the outflow. And there's two contributions to it. One is the angular momentum carried by the gas, RB phi, but there's also net flow of angular momentum due to the magnetic field. Magnetic fields can transport angular momentum and energy. This is associated with the Maxwell stress that Matt wrote down. The R phi component of that Maxwell stress is a flux of angular momentum associated with the magnetic field. So in this problem, we have angular momentum carried out in the outflow, both by the gas and by the magnetic field. The total rate of flow of angular momentum is a constant of integration of the problem. It's a constant of the problem. Okay. So now, to figure out what that constant is, what we can do is we can substitute this expression for the magnetic field into this expression of here. And what you get is the following equation for the azimuthal velocity change. Just a little bit of algebra to show this. Okay. So this is an equation for the azimuthal velocity v phi. It's normalized here to this co-rotating velocity. And you'll notice this is again of the form of one of these equations that has something in the numerator, something in the denominator, where the denominator thingy can go to 0. Okay, if the radial speed equals the radial Alfvén speed, then the denominator goes to 0. Very much like our hydrodynamic solar wind Parker model. This, though, is now the kind of mathematical expression of this Alfvén point that we talked about heuristically here. So Vr, the radial speed of the flow equals the radial Alfvén speed, is this Alfvén point. So this kind of answers the question before of which magnetic field actually shows up in that expression, and it is just the radial magnetic field, and it is just the radial velocity. So if the denominator is 0, we need the numerator to be 0. Yeah. So we need the numerator to be 0. So the numerator is 0 means that the specific angular momentum is the radial Alfvén speed squared, r squared omega, divided by the radial speed squared. But at the Alfvén point, these are equal to each other. That's the definition. So that means RA here is the radius of the Alfvén point, the distance from the star, where the radial speed equals the Alfvén speed. And what this tells us is that this wind solution has uniquely determined how much angular momentum is extracted from the star. So the amount of angular momentum extracted from the star is given by, or this is angular momentum pretty fast, is given by the radial Alfvén speed squared times the rotation rate of the star. And the key thing here, this is really, in many ways, the essential idea behind why magnetized outflows are so important in astrophysics, is that this radial Alfvén speed, which is not high, it's an interesting equation. Okay. Because the magnetic field can be very strong, this radial Alfvén speed can be much larger than the radius of the star. So what that means is the total rate at which the star is losing angular momentum, J dot, is given by the angular momentum per unit mass, L, times m dot, the rate at which it's losing mass. And that means what is the time scale for the star to lose angular momentum? So I can define a spin down time, which is the angular momentum of the star divided by the rate at which it's losing angular momentum, J over J dot. So what is this? Well, this is roughly m r star squared omega divided by J dot, m dot, r a squared omega. So the time scale on which the star loses angular momentum is given by the time scale on which it loses mass, m over m dot, but then it's getting much smaller than that because you have this huge lever arm associated with the magnetic field forcing down the star. So this time scale can be much, much less than m over m dot because the Alfvén radius is large compared to the magnetic field. And that's the essential reason why the solar wind, which is not important currently for taking away mass from the sun, and it has not been in the previous 4.5 billion years of evolution of the sun, is in fact very important for staying down the sun. It's this large torque associated with the Alfvén radius being large compared to the radius of the sun. Yep. So, you mean, so I guess there's several ways, as opposed to what? So this quantity L is actually the net flow of angular momentum out of the outflow. It's a constant, independent of radius. We got L equals a constant by integrating the phi component of the momentum equation. So there's actually a net flow of angular momentum away from the star, which is constant everywhere. So what's special about the Alfvén radius is only that because it's a critical point, I can use it to determine what that constant is. Just like we can use the sonic point to determine what the mass loss rate is in standard thermally driven winds. Yeah, thank you. Good clarification. Okay. So this idea of efficient extraction of angular momentum by large-scale magnetic fields is one that we're going to hear about quite a bit later in the week in the context of understanding jets and accretion disks around particular objects, compact objects, etc. Again, very similar ideas. Okay. So the last thing that I wanted to mention about these magnetized outflows has to do with energy, the energy carried by the outflows. So in hydrodynamics, so if we step back for a second, forget about magnetic field, go back to the first problem. There's a conserved energy per unit mass. It's a constant that is called the Bernoulli constant for those of you who and it's just equal to the kinetic energy 1/2 v squared plus the gravitational potential energy, and then it's plus this thing called the enthalpy, H, where for an ideal gas, the enthalpy is just 5 halves kT over m. kT is the energy per particle, so kT over, say, mass per proton is the energy per unit mass. And what the enthalpy, just remind you from thermo, the enthalpy is the internal energy free half space T plus the PdV work that you can do, plus P over rho. So that's where 5 halves comes from. It's 3 halves plus 1, that's the detail. But that's the conserved energy per unit mass in hydrodynamics. And very roughly, for thermally driven outflows, you can think of this constant is roughly the thermal energy of the corona. So kT corona divided by the mass of the proton. Because what happens if you heat the material up in the corona, it's actually able to escape. Okay. Now it turns out in magnetized wind, there's an additional contribution to the flow of energy leaving the star. So what about magnetized wind? So what's this other source of magical energy leaving the star in MHD? Yes, Poynting flux. You have a magnetic field can carry energy through Poynting flux, so that's exactly right. So there's an additional loss of energy now in the form of Poynting flux, which is again really tapping into the rotational energy of the stars. So what you find then is that the conserved energy per unit mass is this hydro thing, Bernoulli, plus an additional thing, which is the Poynting flux, which I denoted SR, is the radial Poynting flux, that's the subscript R. And then just to get it to have the right units of energy per unit mass, it turns out the thing that matters is dividing by rho times VR. So if you go calculate the Poynting flux like you're used to calculating, what you find then is that this constant is equal to the Bernoulli constant, and then it's minus, so this is, given the magnetic field structure I told you about, it's straightforward to calculate the Poynting flux, so it's R omega VR d phi divided by 4 pi rho. Okay, so I'm going to call this energy per unit mass epsilon. So just like the angular momentum flow in the outflow has both the gas contribution and the magnetic contribution, epsilon has both the gas contribution and the magnetic contribution. This is the gas contribution. This is the magnetic contribution. And in fact, this energy, the Poynting flux carried by the magnetic field, is just equal to the rotation rate of the star times the angular momentum flux carried by the magnetic field. Yep. Yes. Yeah, so the Bernoulli parameter, so we could just as well take it to be adiabatic. Actually, when I wrote down 5 halves kT over m, that was assuming it's adiabatic. There still is a conserved Bernoulli parameter for an isothermal equation state. It's the problem that so this is something I didn't want to go into, but technically what that means is that the velocity of infinity is infinity, and there's a bunch of funny things about that solution that are unphysical. Because you're right, there is a infinite source of energy. That's not actually important for any of these arguments. Okay. So we have both a gas contribution to how much energy is carried away in the outflow, we have a magnetic contribution to how much energy is carried away in the outflow. So the question is, which of these is more important? And one can roughly estimate as follows. So again, just to get a feel very roughly, only parameter is the thermal energy in the corona, the magnetic contribution, which is this omega times the angular momentum flux, remember the angular momentum flux is about equal to this co-rotating Ra squared omega, so this magnetic contribution to the energy flux is roughly Ra times omega squared, which is roughly the co-rotating azimuthal velocity. So the reason for highlighting this distinction is what this means is that there's actually two different classes of magnetized rotating winds. There's one regime, which is the sun, which is the regime where the thermal energy in the corona is much larger than this co-rotation energy. That's a regime in which most of the energy in the outflow comes from the thermal energy of the corona. So that's a thermally driven outflow. So even though the magnetic field is important for extracting angular momentum, the energy of the outflow comes from the thermal energy of the corona. And that's thermally the regime the sun is in. The decrease in rotational energy does not contribute much to the asymptotic energy of the outflow. Most of the asymptotic energy of the outflow is from thermal energy. But there's another regime you can be in, which is the opposite regime. It's the regime, supposed to be energy gas is much bigger than the magnetic energy. You can be in the other regime where the energy associated with the gas is small. This coronal energy is small compared to the magnetic energy. This is the regime in which most of the energy that goes off to the outflow at infinity is actually rotational energy of the central object. So this is what I would call a true magnetocentrically driven or magnetically or rotationally driven outflow, where both the energy and the angular momentum of the outflow come from the rotation of the central object. And this is, for instance, jets, pulsars, permanently rotating stars are all in this regime. So this energy of the outflow is really rotational energy, not thermal. And which regime you're in just has to do really with how much rotational energy the central object has, how strong the magnetic field is, which determines the Alfvén radius, how hot the corona of the object is, etc. But this distinction really demarcates different classes of outflows that you'll see talked about from astrophysical objects. So in particular, what I'd like to stress is that accretion disks are objects where rotation is extremely important, right? It's largely rotating around in a disk. And so in those objects, outflows associated with tapping into the rotational energy turn out to be particularly effective. So that's why you're going to hear a lot later on in the week about magnetically driven outflows from rotating disks, jets, etc. Stars are thermally supported objects, and so they can be more slowly rotating, and so they can be in this regime where the outflows are actually driven primarily by thermal energy. Okay. So any questions about that? That's mostly what I wanted to say about magnetically driven outflows. So there's actually more than it's unfortunately not one. If you want to know one parameter, the one parameter is really the ratio of this thing, Alfvén radius times rotation rate. So that's the speed or rotational speed of the Alfvén radius. So this is thermal energy. But this depends on the magnetic field strength of the central object and the rotation rate of the central object. So it sort of is a one parameter family in this dimensionless number. But this dimensionless number is in turn controlled by multiple things in other systems.